is death? On the 19th of October 1967, Harvard Medical School, HMS, anesthesiologist Dr. Henry Knowles Beecher presented a paper to his university's Standing Committee on Human Studies. It was entitled Ethical Problems Created by the Hopelessly Unconscious Man. In this, he asked a profoundly important question. Under what circumstances, if ever, shall extraordinary means of support be terminated with death to follow? He then went on to add that, when it becomes evident that the brain is dead, there is an obligation to discontinue extraordinary supports. Nair Collins, 2022, page 44. This caused quite a stir, and soon afterwards the Dean of HMS, Robert Ebert, proposed that a special committee should be set up to look into these issues. Under the chairmanship of Beecher, the ad hoc committee of the Harvard Medical School to examine the definition of brain death, alternatively the Brain Death Committee, was set up. The Brain Death Committee aimed to define the criteria regarding irreversible coma and death to serve two purposes: to specify the circumstances of the withdrawal of life-sustaining treatment from those determined to be brain dead, and the procurement of organs for transplantation from such patients. On the 3rd of December 1967, the issue became crucial when South African surgeon Christian Barnard performed the first heart transplant in a hospital in Cape Town. The question arose as to whether during such procedures the donors were dead at the time that the heart was removed, or whether it was the removal of the heart that killed the donors. The subsequent report was published in August 1968. It laid out specific medical criteria that defined the new category of irreversible coma or brain death. These criteria included no movements or breathing, lack of responsiveness, or specific brainstem reflexes. As the years progressed, people became uncomfortable with the decision-making process regarding who lives and who dies. It was felt that a much more precise definition of death was needed, specifically the differentiation between brain death and biological death. Indeed, James Burnett, a neurologist at the Dartmouth School of Medicine in New Hampshire, argued that the two states were identical. A moment's reflection discloses that this is primarily the brain that is responsible for the functioning of the organism as a whole. The integration of organ and tissue subsystems by neural and neuroendocrine control of temperature, fluids and electrolytes, nutrition, breathing, circulation, appropriate responses to danger, among others. The cardiac arrest patient with whole brain destruction is simply a preparation of unintegrated individual subsystems since the organism as a whole has ceased to function. Burnett, 1984, page 48. This argument was accepted, so, in the US in 1981, the Uniform Determination of Death Act, UDDA, defined death as the irreversible cessation of circulatory and respiratory functions, or the irreversible cessation of all functions of the entire brain, including the brainstem. President's Commission for the Study of Ethical Problems in Medicine and Biomedical and Biobehavioral Research, 1981. Since 1981, there has been further refining of these definitions of death. In 1995, the American Academy of Neurology stated that brain death necessitates coma, absence of brainstem reflexes, and apnea, lack of breathing. Subsequently, most US states adopted the UDDA and AAN guidelines. Still, several maintain different standards, which means in practice that a person could be legally dead in one state and alive in another. It is of profound importance with regard to the near-death experience that there has never yet been a case of anyone who has been correctly diagnosed as brain dead who has ever had neurological recovery. But medical science is constantly advancing, and new developments like deep brain stimulation may be able to reverse brain death. And this brings about another huge problem. If death is the separation of the soul from the body, then there must be a moment in time when this happens. A scenario of before and after. One moment a person is alive, the next they are dead. So, we have a concept of the moment of death. Developments in modern science and our abilities to assist the body in continuing to live after fairly traumatic damage suggest that there is no moment of death. It's more a process of death. This is reflected in the central arguments that death is a loss of integrity. So, it must be asked, what is responsible for the integration of the brain if the brain does not function? Integration is impossible, and the soul and the body part company. This integrator theory of the brain has another even more pressing issue. How can we know if the entire brain has ceased functioning? In my previous writings, I have asked, is it the addition of one molecule, one atom, or even one quark that suddenly consciousness pops out of nowhere in a magical cloud of epiphenomena? In 2020, the World Brain Death Project published a report seeking international consensus on the minimum criteria for brain death. Greer, Shemy, Torrance, Varelis and Goldenberg 2020. This report proposed 8 criteria. 1. No evidence of arousal or awareness to maximal external stimulation. 2. Pupils fixed in a mid-sized position and unreactive to light. 3. Absent corneal, oculocephalic and ocular vestibular reflexes. 4. Absent facial movement to noxious stimuli. 5. Absent gag reflex to bilateral posterior pharyngeal stimulation. 6. Absent cough reflex during deep tracheal suctioning. 7. No brain-mediated motor responses to noxious stimulation of the limbs. And 8. Lacking spontaneous respirations during apnea test targets. Effectively, death is caused by cardiac arrest. The heart stops beating and the blood ceases circulating, which means that all body areas cease receiving the oxygen needed. Technically known as ischemia, this is particularly devastating for the brain and its 86 billion or so neurons. Because they cannot store energy, they die quickly. Currently, the modern-day versions of Berger's EEG prototype are the most widely utilised tools to record neurophysiological activity in the dying brain. EEG recordings can be applied in 2 ways in the clinical setting. The first method involves the placement of 16 electrodes spaced equally on the surface of the skull, which can measure surface electrical activity across all brain regions. This is known as the 10-20 system, with an internationally recognised notation of each electrode location on the scalp. The 10 and 20 refer to the actual distances between adjacent electrodes as either 10% or 20% of the total front, back, or left-right distance of the skull. Each electrode placement site has a letter to identify the lobe or brain area being monitored, with a number isolating the placement more precisely. The second method is the so-called bispectral index BIS monitor, and was introduced in 1994 as a way to measure the degree of sedation of the patient. This is of particular importance in the operating theatre, where the surgeon and the anaesthetist need to know that the patient is unconscious and incapable of feeling pain. BIS monitoring consists of 2 to 4 channels placed on the patient's forehead. The sensors receive EEG signals from their respective area and send them to a monitor. This is crucial during surgery, where consciousness during an operation would be intensely distressing to a patient. Known as awareness, this is a critical factor in Gerald Worley's critique of the Pam Reynolds case discussed earlier. BIS analyses a frontal cortical EEG signal which converts into digital data. This data is processed so that an easily comparable score between 0 and 100 is produced. The lower the score, the more sedated the patient is. For example, 0 is total EEG silence, with a BIS value of 40 to 60 when a patient is effectively anaesthetised. This is now known as the Patient State Index, PSI. Over the years, and having been applied to patients in various types of sedation, the PSI has become an essential tool in measuring levels of awareness. But BIS has its drawbacks. For example, because BIS consists of only 2 to 4 electrodes placed on the forehead, it can only measure neuronal activity in that area of the brain. In contrast, the 10 to 20 system can capture all brain areas. So during a death scenario in an operating theatre, BIS could not measure activity in the temporal lobes. Now, if, as I suspect, the temporal lobes are crucial to the near-death experience, then such activity will never be picked up in an operating theatre where BIS is the standard EEG measurement tool. Another problem with BIS is that until recently, it could monitor brain activity in real time, but could not record the activity for later analysis. This has changed with the development of a BIS monitor known as the SedLine Root device by a Californian company called Masimo. This does not overcome the monitor location difficulties of BIS, but it has allowed records of brain activity to be kept when the patient dies. It was a SedLine Root monitor that recorded an extraordinary case of brain activity after death. In 2009, Washington-based anesthesiologist Dr. Lakmir Chawla and his associates published a paper in which they described how they were able to capture a raw EEG signal in a patient who had just died. Chawla, Junker, Jacobs, Seneff and Axt, 2009. This was part of a study on end-of-life neurological activity. They reported on 7 critically ill patients who, for various reasons, had had life support removed. The case involved a patient whose brain activity was recorded by a SedLine. As we have already discovered, one of the most valuable aspects of the SedLine is that it can measure and record EEG signals. What Chawla and his team found when they checked the recordings was intriguing. They noted that after the patient had died, the SedLine recorded a sudden surge of gamma wave activity. You will recall earlier that gamma ray activity is consistent with cerebral arousal, and this is precisely what Chawla et al. Observed in the recordings. A multitude of these BIS spikes, greater than 20, in other patients who were immediately antemortal, and the timing of these spikes is consistent, although not all patients will demonstrate a surge of activity. Chawla, Junker, Jacobs, Seneff and Axt, 2009, page 1097. The term antemortal is crucial here. It's another way of saying after death. So, brain activity involving awareness was measured and recorded after the patients had died. What is intriguing is that this was not the first time a BIS spike had been observed but not recorded in a similar clinical setting. In 2005, a BIS monitor detected a massive spike in brain activity as a 79-year-old woman began the dying process. Although this was not post-mortem, it is again evidence that the activity starts before brain death and continues afterwards. Gambrill, 2005. This is supported by several clinical and experimental settings involving human and animal subjects dating back to the mid-1980s. Clute and Levi, 1990, Hansen, 1985. Chawla et al. Stated that the BIS spikes observed with their 7 patients lasted between 30 and 180 seconds. The team was concerned that external electromagnetic interference may have caused the spikes. However, they argued that the constant similarities of timing observed in each patient and different environments suggest that this was not the case. They added that electrical activity that was not strong enough to cause physical movement in the patients and yet sufficient to generate electrical activity in the brain was also doubtful. Interestingly, the team argued that this brain activity prior to death may be the source of many of the reported near-death experience traits that we discussed earlier. These include the out-of-body experience, OBE, and the panoramic life review. Although not referenced directly, it is likely that, among others, the Chawla et al. 2009 paper inspired, at least in part, the research of neuroscientist Jimo Borjigin and her team at the University of Michigan in 2013. Borjigin, J., 2013. In their abstract, the team explained that they were keen to understand how, during a near-death experience, a malfunctioning and oxygen-starved brain can create images of such lucidity and vividness. To do this, they monitored EEG signals from rats in 3 states of awareness: wakefulness, anaesthetization, and cardiac arrest. The electrodes were implanted in the brain rather than the usual surface electrodes used in the standard 1020 EEGs. This gave a far more accurate reading of brain activity with much less chance of external electromagnetic interference. After the first wakeful measure was taken, the rats were anaesthetized, and the second measure was taken. When fully unconscious, the rats were placed in a state of cardiac arrest. To their surprise, the team observed a massive increase in gamma wave activity in the dying rats, together with the phenomenon known as coherence. This is when all the different wave frequencies in the brain become synchronized. As we have already discovered, gamma wave activity suggests heightened, not declining consciousness. But even more astonishing was that the global coherence of lower gamma oscillations in the 35 to 55 Hz range continued for more than 15 seconds after the rats were clinically dead. Further tests in which the rats were killed using carbon dioxide inhalation induced a similar surge of global coherence. The paper states, "Our results clearly show that mammalian brain activities become transiently and highly synchronized at near death." Borjigin, J. 2013. As I discuss in greater detail in my previous book, Cheating the Ferryman, The Revolutionary Science of Life After Death, Peake 2022, pages 145 to 149, of possible significance here are the similarities between the surge of brain activity recorded in the dead rats' brains and a temporal lobe seizure. As previously discussed, gamma waves are the fastest brain waves possible, oscillating from 35 Hz up to 100 Hz. This would mean that everything perceived by the rats during such brain activity would be hyper-real. Their sense of time would slow down profoundly, especially regarding the temporal flow perceived by an observer experiencing standard brainwave frequencies. In effect, this means that if the rats could perceive anything in this seemingly dead state, a second of normal time would be perceived as a much more extended period, possibly hours, weeks, or years. As we have already discovered, this is precisely what is reported during near-death experiences and by individuals with other neurological conditions. These are also the perceptions reported by individuals experiencing temporal lobe epilepsy, aura states. It has been discovered that gamma wave activity in the brain is directly related to TLE seizures. Hughes, 2008. This presents a direct link between Borjigin's findings, TLE, and NDE. It is essential to add that, in October 2013, Jimo Borjigin, Michael Wang, and George Masur, in a letter published in the journal Biological Sciences, replied to Chawla and Seneff's paper, Borjigin, Wang, and Masur, 2013. In this, they agreed with the importance of gaining a scientific understanding of the dying process. They took issue with Chawla and Seneff's claim that Borjigin's earliest paper had largely confirmed their conclusions that end-of-life electrical surges could be responsible for the near-death experiences. Borjigin et al. Argued that the two groups used different EEG devices and that the BIS monitors and the SED line had been designed to monitor depths of anesthesia during surgery and had not been validated for monitoring features of conscious information in waking humans, adding that the parameters used in their study had been. They finished the letter by stating, "To compare our studies with those using the BIS or other monitors, one must perform the two kinds of analysis simultaneously in the same individuals, rats or humans. This type of study may bridge human and animal studies and facilitate the understanding of the neurophysiology of the dying brain." Borjigin, Wang, and Masur, 2013. There was a degree of disagreement on the implications of these results. Not deterred, in 2017, Dr. Chawla, with another group of associates based in Washington, D.C., expanded upon his 2009 paper by describing some new research he had been involved in regarding end-of-life electroencephalographic surges in critically ill patients. Chawla et al., 2017. In the introduction, Chawla and his team discuss how the end-of-life surges that Chawla et al. Had discussed in their 2009 paper have now gained their own acronym, ELES, End-of-Life Electroencephalographic Surges. Additionally, the discoveries of Van Rijn et al., Van Rijn, Kreinen, Menting, Hemling, and Konin, 2011, and Jimo Borjigin et al., Borjigin, J., 2013, had effectively proven that the surges could not be attributed to external influences, but were EEG signals emanating directly from the brain being monitored. Indeed, a second independent report of ELES from 2010 showed that an ELES tends to occur 30 to 180 seconds after the loss of blood pressure in the body and lasts between 15 and 240 seconds. Ayong et al. 2010. Chawla et al. Examined the medical records and raw EEG data of 35 terminally ill patients undergoing palliative care at the ICU at George Washington University Hospital. Of the 35 patients, 13 had ELES recorded. The team concluded that they had demonstrated that ELES are common in patients who die in the ICU. Chawla and Seneff, 2013, page 5. One of the team was able to observe an ELES taking place as the patient died. They reported that the patient appeared unconscious with no signs of any movement, and yet the neuromonitoring showed that the patient was in a state of full consciousness. From this, it can be assumed that had such levels of awareness been recorded in the brain of a person undergoing surgery, extreme actions would have to have been taken to avoid powerful trauma, both physically and psychological. Indeed, what implications does this have for cases such as Pam Reynolds's? In their conclusion, they cited supporting evidence from the findings of Jimo-Borjigin et al., stating that this demonstrated cohesive gamma-wave electrical activity after death. Chawla and Seneff, 2013, page 8. They also asked why it is that while approaching 50% of terminally ill patients experience ELES, a small but significant number do not. If it was, as they describe, an evolutionary last gasp survival mechanism, why are ELES not found in all cases? And, of possibly even more significance, why is ELES never observed in patients who are diagnosed as being clinically brain dead? However, I can confirm that Pierpaolo Pani and his associates presented further evidence for postmortem brain activity at Sapienza University in Rome in 2018. In a letter published in the journal Resuscitation, they reported they had observed the presence of cortical electrical activity persisting for about 2 hours after death by cardiac arrest of an adult male macaque monkey. As with the human patients of Chawla et al., the spike in activity started before death and continued afterwards. What is fascinating about this discovery is that Pani et al. Stated in their abstract that, importantly, this activity appears after a period of relative silence, and it is characterized by a peculiar temporal relationship between LFP and MUA in several electrodes, suggesting a non-local origin. Pani, Giacoga, Brunamonti and Stefano, 2018. Interestingly, in the letter, Pani et al. Argue that their discovery of the 120-minute post-mortem cortical electrical activity contradicts the tens of seconds reported by Jimo-Borjigin and her team at the University of Michigan in 2013. Borjigin, J., 2013. In this respect, we need to discuss a series of related but morally questionable decapitation experiments that were undertaken by Clementine Van Rijn and her associates in 2010 and reported in January 2011. Van Rijn, Kreinen, Menting-Hemmeling and Kernan, 2011. In justification, it seems that the series of experiments involving the beheading of live rats was to decide whether such a process is a humane method of euthanasia for awake animals. The experimenters decapitated 22 male Wistar rats aged between 6 and 8 months. 9 rats were guillotined while fully conscious and 8 were anaesthetised. During the procedure, all the animals' brains were monitored with an EEG before, during and for at least 5 minutes after execution. The results were startling. It took an average 17 seconds for the electrical activity in the decapitated brain of the previously awake rats to flatline, technically known as being isoelectric. Furthermore, the post-decapitation brain activity was similar in awake and anaesthetised animals. One conclusion was that the animal's consciousness is briefly enhanced immediately after the neck cut. In other words, an anaesthetised rat's previously unconscious brain becomes aware after it is decapitated from its body. But what was totally unexpected was that it was discovered that around 50 seconds after the decapitation, when the brain is in a state of isoelectricity, a large amplitude wave suddenly appeared. This differed slightly between the previously awake rats and those who had been anaesthetised. For the latter group, the wave appeared after 80 seconds. Interestingly, the authors noted similarities with the findings of Chawler's 2009 experiment. In the summing up of their findings, the team coined the terrifying phrase, the wave of death. The wave thus might reflect a massive opening of ion channels, a depolarization wave. The still functioning of these ion channels in the period before the wave might be responsible for the observed difference in the pre-wave and post-wave power of the EEG. Hence, it is thought that the wave represents the synchronous death of brain neurons expressed in a wave of death. Van Rijn, Kreinen, Menting, Hemmeling and Kernan, 2011. In 2014, a group of New Zealand-based researchers at Massey University followed up on the findings with a similar experiment to Van Rijn's et al. This time, all 10 rats were anaesthetised and then beheaded. Again, at around 15 seconds after decapitation, significant increases in brain activity were noted, specifically in 2 areas of the EEG power spectrum at the median frequency, F50 and F95. Kongara, McAloon, Kells and Johnson, 2014. In 2015, Bourjigin continued her research in this critical area and, together with a large international team, she published an article in the academic journal Neuroscience. In this, the team found consistent heart rate changes in rats undergoing experimental asphyxia, including 4 distinct stages, starting with the onset of asphyxia and ending in ventricular tachycardia and asystole. Lee et al., 2015. The team made a series of continuous electrocorticographic recordings using electrodes implanted in the rat's left and right frontal, parietal and occipital lobes. These revealed increased coherence in the gamma band, 65 to 115 Hz, and the theta band, 5 to 10 Hz, between all cortical sites, with increased functional connectivity between the frontal, parietal and occipital cortices in multiple frequency bands. The degree of connectivity between neural networks, feedback and feed-forward directions in which network connectivity between brain regions increased, and the frequency band in which connectivity was principally observed, varied consistently in relationship to the stage of asphyxia. Dramatic surges in the levels of multiple neurotransmitters were reported, including norepinephrine, serotonin, dopamine, GABA, and acetylcholine in both the frontal and occipital cortex, and levels remained elevated for as long as 20 minutes following the onset of experimental asphyxia. They conjectured that surges in neurotransmitters in the first minutes of asphyxia may help explain widely reported features of NDE phenomenology. They postulated that the observed 30-fold increase in central norepinephrine might be consistent with transiently increased alertness, attention and arousal. A 12-fold increase in central dopamine may be consistent with increases in arousal, attention, cognition and affective emotions. And a 20-fold increase in central serotonin may help explain visual hallucinations and mystical experiences. The authors inferred that the observed surge in synchronized cortical gamma activity stimulated by asphyxia signifies an internally aroused brain and supports the hypothesis that the mammalian brain is capable of high levels of complex information processing at near death. In relation to these findings, further support was supplied in February 2022 when a paper appeared in the peer-reviewed academic journal Frontiers in Aging Neuroscience, Vicente et al. 2022, under the reasonably innocuous title of Enhanced Interplay of Neuronal Coherence and Coupling in the Dying Human Brain. The article described what may be one of the most astonishing discoveries about what happens in the dying human brain in the history of science. What was also of interest was the geographic scope of the authors, who were located in China, Estonia, Canada and the USA, and were describing an event that took place in Germany involving an 87-year-old Canadian male who was being treated in a hospital emergency unit after a fall in which he sustained a head injury. After a series of tests, it was concluded that his Glasgow Coma Scale, GCS, was 15. The GCS is the most common scoring system used to describe the level of consciousness in a person following a traumatic brain injury. It is used to help gauge the severity of an acute brain injury. 15 is considered to be very minor. However, he rapidly deteriorated to a score of 10, which concerned the attending physicians. Although his gag reflexes and his corneal reaction was preserved, one of his pupils was much larger than the other, an effect known as aniscoria. Under a CT scan, it was discovered that he had several bilateral acute subdural hematomas, areas of bleeding in the outermost layer of the brain between the inner surface of the skull and the surface of the brain. He was operated on to clear the blood and was stable for 2 days before he declined again. An electroencephalography EEG scan was obtained, which showed that his left hemisphere had gone into a state known as status epilepticus, in which a series of epileptic seizures take place one after the other. In this case, at least 12 were recorded. His breathing then became very laboured. It was agreed with the family that a DNR, do not resuscitate status, be applied, and soon afterwards the patient died. During this time, his brain continued to be monitored using the EEG, and what they discovered was astonishing, as was reflected in the introduction to the paper. Here we report what is to our knowledge the first continuous EEG recording from the human brain in the transition phase to death. We find decreased theta activity and an increase of absolute gamma power after bilateral suppression of neuronal activity. Post-cardiac arrest, relative gamma band power is increased, while delta, beta and alpha bands show reduced activity. Finally, we observe strong modulation of narrow and broadband gamma activity by the alpha band. This is of significance. There was a decreased theta activity and an increase in absolute gamma power as cardiac arrest started. This is, in layperson's terms, the point of death. Post-cardiac arrest means after the person had died. In the discussion section, the authors refer to the papers by Bourgigin et al. 2013 and observe the similarities. Bourgigin and her associates made a point about how, in the dying rodents, an increase of low gamma band frequencies was observed 10 to 30 seconds after cardiac arrest, but there were intriguing and possibly significant differences. One of these can be observed when comparing phase amplitude coupling, cross-frequency coupling, post-cardiac arrest, delta, theta and alpha modulate low gamma activity in the rodents, Bourgigin et al. 2013, whereas in the human brain, such modulation occurs in all gamma bands and is mainly mediated by alpha waves and to a lesser degree by theta rhythms. The alpha band is thought to critically interfere with cognitive processes by inhibiting irrelevant or disrupted networks. This is so because it is known that the cross-coupling between alpha and gamma activity is involved in cognitive processes and memory recall in healthy subjects. And then the authors throw in this incredible observation. It is intriguing to speculate that such activity could support a last recall of life that may take place in the near-death state. This is precisely what I suggested may have been happening with Bourgigin's rats in my last book, Peake, 2022, pages 145 to 149. But it is important to note that a degree of caution in overreacting to this discovery was argued by NDE luminaries Bruce Grayson, Pim van Lommel and Peter Fenwick in a commentary on the paper published in the same journal on the 18th of May 2022, Grayson, van Lommel and Fenwick 2022. They argued that the EEG recordings as described did not show an absolute gamma activity increase after cardiac arrest. Indeed, it showed a decrease, pointing out that only the relative amount of gamma increased compared to alpha, beta and delta. Also, increased gamma and gamma synchronization are not exclusively related to consciousness perception, but have been observed in several brain activities. Mutha Kumaramaswamy, 2013. They also suggested that the gamma wave activity could have been caused by muscle contractions, pointing out that this type of contamination is well known. Indeed, a few years earlier, in 2013, and in response to Bourdieu's original paper, Bruce Grayson was again determined to question the idea that the discovery of brain activity during the cardiac arrest of rats could be associated with the near-death experience. He questioned the use of the term hyper-aroused with regards to the rat's brains, and argued that what happens in a rat's brain may not apply to a human brain. Although these points seem reasonable, I cannot help but feel that the enthusiastic way in which Grayson et al. Are willing to dismiss the findings of Vicente et al. May be related to the fact that all three are very much advocates of the survivalist position with regards to NDEs, and any form of neurological explanation based on brain activity suggests that the NDE is a brain-generated phenomenon. Indeed, I find it curious that Dr. Fenwick, whose own book, as we have seen earlier, is full of experiences of the panoramic life review, for example, the much-cited case of Alan Pring, who was given glimpses of what can only be described as a speeded-up video of his future life, Fenwick and Fenwick, 1995, pages 120 to 121, takes this stance. Is it not more likely that the source of such information is brain-programmed memories than something outside of the experiencer's brain? The latest research exploring this crucial area was described in a paper published on the 1st of May 2023 in the journal Neuroscience. Gang Zhu and a group of neuroscientists, again including Jimo Bourdieu, described how the team investigated further evidence for the brain's gamma oscillations and functional connectivity at the point of death. They analysed the electroencephalogram and electrocardiogram signals in 4 comatose dying patients before and after the withdrawal of ventilatory support. The objective of this study was to discover if there is any evidence of high-level awareness in the brains of dying patients, awareness that could justify the perceptions reported by near-death experiencers. For example, there is evidence that the visual and hearing systems in the brain are fully functional, or at least functional enough to create dream states. It has been discovered that the stimulation of 2 brain areas, the occipital and parietal cortices, can create visual images that have no relationship with any external visual stimulus. Mazzi, Mancini and Savazzi, 2014. This can be linked with how it is known that the temporal and parietal cortices are crucial to perceptual awareness. From this, it can be concluded that the area where these 3 cortices come together, the temporoparietal occipital TPO junction, is where visuospatial processing occurs. Indeed, it has been shown that this area is involved in dreaming, Scolari et al. 2017. We discussed this area extensively earlier in our inquiry, and it is now evident that some crucial correlations have been drawn. However, the most exciting thing is how these discoveries can be linked to the earlier referenced Bourdieu et al. Paper from 2017. In their summing up, the team made the following comment regarding the findings. Our results clearly indicate that mammalian brain activities become transiently and highly synchronized at near death. Bourdieu 2013. So whatever the near-death experience is, it is part of the dying process, or, more specifically, what happens in the brain as it prepares for death. This does not mean it is not a real event, as modern quantum mechanics tells us that reality is a slippery concept. However, from our present understanding of neurology and neurochemistry, a model of dying can be formulated, which is most neurologists' position. They believe that their dying brain hypothesis successfully explains the NDE. It is my task to present you with the facts supporting this model and allow you to decide whether the case is made.